On Chapter 4, today we're going to talk about isotopes and atomic mass. So isotopes are atoms of the same element that have different mass numbers. Last time we were talking about how to figure out the number of protons, neutrons, electrons in an atom from the information on the periodic table. But not all atoms of an element are the same. Sometimes they have different numbers of neutrons. They will always have the same number of protons, right? The number of protons identifies the element. So like this is a strip of magnesium. Anytime we have magnesium, it will always have 12 protons because that's what makes it magnesium. And it will always have 12 electrons if it's neutral because our protons and electrons need to be equal. However, it can have different numbers of neutrons. And if it has different numbers of neutrons, then that will actually change the mass number. So if you'll look, we have different isotopes shown down here at the bottom. The way that we write this notation, when we have it, right, if we have magnesium, the atomic number will go on the bottom, right? This is the atomic number or number of protons. And then the mass number will go on the top. Our most common isotope of magnesium is magnesium 24, which is why we see the mass on the periodic table is really close to 24. But there are other isotopes of magnesium, which is why that mass is 24.31 instead of being exactly 24. This this decimal number tells you that there are some isotopes of magnesium that are actually higher in mass. So we have magnesium 25 and magnesium 26. Regular magnesium would have 12 neutrons, right? 24 minus 12 gets us 12 neutrons. But magnesium 25 will have 13 neutrons, and magnesium 26 will have 14 neutrons. So the number of neutrons is changing in all of these, which is why we have different mass numbers. So again, when we're looking at this, this is going to be our chemical symbol, right? Mg stands for magnesium. The number on the top will be the mass number, and that's always going to be protons plus neutrons, right? Total. And then the atomic number will be on the bottom. That will be the number of protons. Make sure you never write this as a decimal number. This always needs to be a whole number because this is a mass number. Remember, atomic mass has decimal points. Mass number does not. So again, all of the isotopes of magnesium have the same number of protons. That's why this number on the bottom is the same. But the number on the top is different because they have different numbers of neutrons. That's causing them to have a different mass number. Okay, so that's how we will recognize that these are different isotopes. The number on the bottom, the number of protons is the same, but the number on the top is different. So here, if we look, just to get some practice with this type of notation, we could figure out the number of protons, neutrons, and electrons in each one of these. So like oxygen has a number 8 down here. That means it has 8 protons and 8 electrons, right? It has 8 protons because that's what the number 8, and the 8 electrons will be equal to it because it's a neutral molecule, or a neutral atom. And then we know it has 8 neutrons because we have 16 minus 8 gives us 8. Phosphorus, we have 15 protons from the number on the bottom. And remember, the number of protons will equal the number of electrons because it's neutral, so 15 protons and 15 electrons. And then we have 31 minus our 15 protons will give us 16 neutrons. And then lastly, zinc, that number on the bottom that tells us the number of protons. Protons are equal to electrons, so we also get 30 electrons. And then we can do mass minus our number of protons will get us our neutrons. Okay. Go ahead and find your Chapter 4 lecture worksheet and complete problem number 14 to get a little practice with this. Okay, so this was problem 14. And so again, the number 6 on the bottom tells us that all of these are carbon. They all will have 6 protons and 6 electrons. The number on the top is different, which means that they are different isotopes. And again, we can subtract those to figure out the number of neutrons. So 12 minus 6 will give us 6, 13 minus 6 gives us 7, 14 minus 6 gives us 8. Sometimes, as you'll see, it's written up here. Sometimes we'll leave the number on the bottom off because it says that it's carbon, right? And anytime it's carbon, the number on the bottom will always be 6. So that's just kind of redundant. So if you ever see it without the bottom number, that's okay. The number on the top is the one that's important because it's different isotopes. Anytime it has a carbon, we can go and we can figure out the number on the bottom should be 6. Okay, go ahead and work on problems number 15 through 20 on your Chapter 4 lecture worksheet. That will give you a little bit of practice with this isotope notation and identifying different isotopes. Okay, so the atomic mass of the element, that's the number that's on the bottom. So if you went and looked at the periodic table, you would see like this one, right? This is sodium. Sodium is atomic number 11, and its atomic mass is 22.99, which is not a whole number. We've been talking about thus far that our mass numbers are always whole numbers because it's protons plus neutrons, but the atomic mass is determined a different way. Okay, it is calculated based on the weighted average of all of the naturally occurring isotopes. This is not the same as a normal average. It's not like add them all up and divide by 3 or whatever it is. This is a weighted average, and a weighted average is based on how frequently you find those particular isotopes in nature. So if you find, carbon 12, which is a really common isotope of carbon, right, that would have the highest weight because it's the most common, whereas carbon 14 is really rare, so it would have a lower weight. And I'll show you how to calculate this. So, but again, this is not the same as mass number. This tells you, on average, the mass of an atom of, in this case, sodium. So go ahead and do problem 21 on your Chapter 4 lecture worksheet. This is just identifying the atomic mass of each element. Okay, so if you look at the periodic table, the masses are pretty much not whole numbers. We have, usually there's something like you'll see for lithium, where it has 6.941 AMUs. It's really close to 7, right? But it's a little bit lower, and this is because most of lithium shows up as lithium 7, but some of them are lithium 6. So on average, it's going to be just under 7 because it's close to 7, but not quite completely. You'll see that fluorine has a whole number here, right? Because fluorine is only having that one isotope. So that's why we're seeing closer to a whole number. Oxygen, you'll see close to a whole number too. This is actually like 15.9994. And so this is because most oxygen is oxygen 16, right? But we have some of it that's oxygen 17 and 18 and so on. Okay, so all of these are not whole numbers because they are not, there are more than one isotope. Okay, over to the right here, this tells you the most prevalent isotope, and you'll see for the most part, if we have, the most prevalent isotopes, so like copper 63, that's why this mass is similar to copper 63 versus copper 65. Like this, we have sulfur 32, that's why this mass is closest to 32. Okay, so you can figure out the most prevalent isotope based on this atomic mass. 3 naturally occurring isotopes. And we were talking about earlier that it has an atomic mass of 24.31 on the periodic table. And so that's really close to magnesium 24. And if we look at the percent abundance down at the bottom, we'll see that magnesium 24 has the highest percent abundance, right? It's almost 79%. That's why our mass here is the closest to magnesium 24 because it has the highest percent abundance. And it's a little bit higher than 24 because the other 2 isotopes have masses higher than 24. So we have magnesium 25 and magnesium 26 that are pulling that average mass a little higher. Okay, so like I said before, the percent abundance can be used, the molar mass on the periodic table can be used to figure out the most abundant isotope. So today we're going to talk about how to calculate that atomic mass. And you need 2 things to calculate the atomic mass. You need the percent abundance for each isotope. And again, that's the number on the bottom. That's how frequently it's found in nature. And you also need the atomic mass of each isotope of that element. Sometimes it will give you the mass number. Sometimes it will give you the atomic mass. But if you'll look, right, the mass of the isotopes, they're all very close. Like this would be 24, 25, and 26. So they'll always be close to some whole number. So you may get the atomic mass of the isotope, which would have a decimal, but you may get the mass number. And so then to calculate it, we have an equation. So our average mass is going to equal the mass of the isotope times the percent over 100. And you're just going to keep doing that, mass times percent over 100, for as many times or as many isotopes as you have. And then when you're going through and calculating this, I would punch this into your calculator, then punch this into your calculator, right? And so on, and then add them all together later to avoid any calculation errors. So let's see an example, right? We have chlorine 35 and chlorine 37. If we had, the masses of each of these, right? So we have the masses and their percent abundance, right, down at the bottom, we could go through and we could calculate the average mass of chlorine. And the way that we would do this, we would do, so our mass would equal 35, and then our percent for chlorine 35 would be 75.76 over 100, plus the mass of our other isotope, 37, times its percent abundance, 24.24, over 100. And we could calculate those, right? We could math all that out, and that would give us 34.45 AMUs, which is the mass on the periodic table. So here it is. So this one, right, we have an actual masses. So again, we do our mass times our percent over 100, our mass times our percent over 100. And this is the same problem from the one before. The only difference here is that we have the actual masses of these isotopes. So we'll put mass times percent over 100, mass times percent over 100. And then, like I said, I would math this, right? Multiply the top, divide the bottom, and then get a number. And then math this, multiply the top, divide the bottom, get a number. And then I would add them together. I have found that people are the most successful doing it that way rather than trying to use parentheses and fit it all in your calculator all at once. And then, like I said, if you add those together, you will get your answer. Let's try another one. So this one says, calculate the atomic mass of an element with the following isotopes. So here we have mass numbers instead of atomic masses. So oxygen 17, whenever it's written like that, like if we have this. So this will always be the name of the element. This number, this will always be the mass number. Okay, so if you see it written as oxygen 17 or oxygen 15 or oxygen 16, that's telling you the mass. So oxygen 17 has 6% abundance, so we do mass times percent over 100. Oxygen 15 has 13% abundance, so we do mass times percent over 100. Oxygen 16 has 81% abundance, so again, mass times percent over 100. And then you'll go through and you will plug each one of those into your calculator. So when we plug in this, we get 1.02, 1.95, 12.96. And then we can go through and add them together, 15.93 AMUs. Okay. Go ahead and try problems 22 through 25 on your Chapter 4 lecture worksheet. This will give you some practice doing these calculations with atomic mass.